Okay. So the definition of so now what we're going to do is the definition of self-adjoint operators. So far we looked at maps, right? We looked at linear maps that are going from V to W. Now we look at things that go from V to V. Okay, so we're going to look at maps this time. Sorry, operators instead of maps, right? Is this fine? Okay, so the definition of self-adjoint in this case is going to be as follows. So we're going to say that an operator T in the set of operators is self-adjoint if T equals T star. That is, so one can write down the condition more precisely. So one can say TLV is self-adjoint if and only if what holds TVW is the same as VTW for all VW in the vector space. Is that okay? Is the definition okay? Okay. All right. So let's quickly look at an example. Right. So in this example, it says you take this matrix. So we have a matrix 2, B, 3, and 7. Okay. And we want to find all numbers P such that T is self-adjoint. Okay, so how would we approach this question? So we know that the definition is what? The definition is that T has to be equal to T star. Right? That's the definition. And remember in the previous theorem, right, we had a characterization for the matrices of T. So if I give you a matrix for T, how would you construct the matrix for T star? How do you construct conjugate transpose? Okay. So here so if this is say the matrix for T, what would be the matrix for T star? It would just be the conjugate transpose. 7, 3, you'll have T star. Okay. Okay, and if we require T star equals T, the matrices would have to match, and then you would have B star equals 3. Okay. Is that okay? Is the example making sense? Yes. This is really straightforward. We're not really doing anything very complicated. Okay. Now, so let's continue then. So it says that one can easily verify that the sum of two self-adjoint operators is self-adjoint. Okay, so sum of self-adjoint is also self-adjoint. Okay, this is sort of easy to see just because of linearity and things like this. One can quickly check. Okay, and the second part is the product of a real scalar and a self-adjoint operator is also self-adjoint. Right? So if it is the case that T equals T star, then of course if you multiply it with some real number R, then this is also going to be the case, right? There's nothing very complicated about this, right? All right. Okay, so now it says a good analogy to keep in mind, especially when we are in the field of complex numbers, is that the adjoint on the set of operators plays essentially a role analogous to complex conjugation on C. Okay, so in the field F equals C, the role of complex conjugation, okay, is analogous to that of the adjoint, or rather the other. So the role of the adjoint on the set of linear operators on V is analogous to the role of complex conjugation. Okay. Very simple. Okay, so we know that a complex number is real. So a complex number Z is real if and only if Z is Z bar. Right, this is just straightforward. Now, what can one say about the self-adjoint operator? Right. So for self-adjoint operator, if you have T equals T star, then T behaves like a real operator. So behaves like a real operator. Okay, of course, I'm not making this very precise at this point, but that is sort of the intuition. So that is why we are saying T equals T star and these operators. Okay. So now we'll see that the analogy discussed above is reflected in some important properties of self-adjoint operators, beginning with eigenvalues. Okay. So here I just said behaves like a real operator. I didn't tell you what that means. What we'll see is that there are lots of properties that would turn out to behave like real numbers. Because in particular, we see that eigenvalues will turn out to be. Even though the matrix itself can have complex entries, the eigenvalues will turn out to be things like this. Okay. Okay. So let's see. And if f equals r, then by definition every eigenvalue has to be real. Okay, you may not be able to find eigenvalues always, but if you do, it has to be real. And so basically the theorem that we're going to write down now is only interesting when the field is complex numbers. Is it making sense so far? Sorry. All right. Right. So let's take the theorem. So the theorem here says the following. So this is theorem 7.13. So the theorem basically says that, as I was already mentioning, every eigenvalue of a self-adjoint operator is real. Is it okay? So the definition of self-adjoint was T equals T star. And we are asserting that if an operator satisfies this property, then the eigenvalues are real. Is it okay? All right, so let's see how we would prove something like this. So we're going to sort of use the inner product property, right? That so the property was that TBV is going to be the same as VTB, right? This is sort of the main property. We're going to use this. So let's see how the proof works. So suppose T is a self-adjoint operator on V, okay? And let lambda be an eigenvalue of T, okay? And V, or well, I've written it as V, sorry. So let V be a non-zero vector in the vector space such that TV equals lambda. So basically V is the eigenvector and lambda V is the eigenvalue. Right? So we're just assuming that such a thing exists. So this is eigenvalue, this is eigenvector. Right? And now we are saying what? We are saying that we're going to consider the following. So we'll write lambda norm of V. Okay, we consider this object, lambda norm of V. How can we write this? So remember the definition of norm was what? It's the inner product with itself. Okay? So lambda norm of V, right? And we can pull the scalar inside. This is fine. So we have lambda V, correct? Okay. Now we can use this equation over here. Right? So lambda V one can write as T times V. So we have TV V, correct? So far so good. Okay. Now here, because I use this property over here, and now I'm going to use the fact that the operator is self-adjoint, right? So remember, self-adjoint was this property over here. Okay. So I'm going to use star and write it as what? We'll write it as V comma T. If it was not self-adjoint, what would we get? T star, right? But since it is self-adjoint, we don't have to write the T star. We can just write T. And now again, we know that TV is equals lambda, right? Because it's an eigenvector, right? So now you will have V lambda, correct? And this one can essentially pull out. But when you pull it out now, you're pulling it out from the right hand side of the inner product, not the left hand side. So you're going to pull it out for the complex conjugation. Right? So you'll have lambda bar V, right? And what is VV? It's just the norm of V squared. Is that okay? And so what does that show you? So the vector was non-zero, right? This we assumed obviously it's an eigenvector, and eigenvector can never be zero by definition. So therefore, what do we conclude? We conclude that lambda has to be the same as lambda bar. And what does that mean? The eigenvalue is reasonable. It's a very simple thing. Okay. Any questions about the proof? All good, right? These are very straightforward things. Like once you know how to do it, it's not that difficult. Of course, thinking about it for the first time may be hard. So That is the only non-triviality here. Okay, so let's continue then. Now the result says that over complex numbers, TV is orthogonal to V for all V. Okay, so the next result, so this is the one that we're going to write down now. I haven't written it down. So what does the next result say? It says that if you're in the complex field, so over the field of complex numbers, TV is orthogonal. Okay, so you take some vector V, you apply it on you apply the operator T on it, you'll get some new vector. So this vector is orthogonal to the original vector that you started with, okay, for all V. Okay, this property only holds for the zero operator. So if this property is true, then zero. Yeah, that can only happen if T is the zero operator. Okay, that is what the result is that we're going to prove in just a moment. Okay, so let me say the statement again. The statement is saying you pick any vector you want, any vector V, you apply the transformation on it, you'll get a new vector. These two vectors are orthogonal. You're guaranteed. Okay, so the operator T is such that these two vectors are orthogonal regardless of which vector you start with. Okay, if that property is true, then it must mean that this T operator is the zero operator. That is the only way to do it. Is that okay? If was it a, no? I forgot your initial J, right? J. Is it making sense? Okay. So that is the statement, which we'll prove in just a moment. Okay. So we'll prove it in just a second. The interesting thing is that this result only holds when your field is complex. When your field is real, this result is long. Okay. And here's a very interesting example. So what one can do is, so one can, okay, so let me write this down. So this result is false. It's false when f is real. Okay. So why? So let's look at an example. Let me make a little bit more space for myself. Give me a sec. Okay, so why is that? So suppose that T is a linear operator in R2. Okay. That is a counterclockwise rotation. So counterclockwise rotation by 90 degrees. So right, so you're just defining an operator that does a counterclockwise rotation by 90 degrees. Okay, and you're in R2, so you're in 2D space. Okay, so clearly, whatever. Okay, so what more precisely you have Txy is the same as minus yx. Okay, that's just algebraically what you do, right? And now it's clear that TV is orthogonal to V. Right? Because you took a vector and you rotated it by 90 degrees counterclockwise. So regardless of which vector V you take, TV is always going to be orthogonal to it, correct? And it's not the zero vector, right? While the theorem was saying that if this property holds that for all vectors, the resulting vector, once you apply T, is orthogonal, then the vector has to be zero. So obviously that property is not true. Yeah. So we will look at the theorem proof, and then I'll leave it as an exercise for you to check why it fails on the example. Okay. But let's see. That's a very good question, right? Like it looks like it should be true. So we will see what goes. Okay. Any questions at this point? Is the statement more or less clear? Why it doesn't hold for reals is clear. Yeah. Okay. All right. So let's continue then. So what is the statement here? So it says, so theorem says, suppose V is a complex in a product space. Okay, and you have some operator T in this on this set of operators on this vector space. If we have the property TV, V is zero for all V in the vector space, that implies T is zero. Yeah, actually, I may have written the implication the other. I think this part is kind of obvious already. So I wrote the wrong direction. Right? The non-trivial direction is backwards, right? Of course, with the zero vector, everything is orthogonal. There is nothing to do. Sorry. Okay. Making sense? Okay, so I had written that if it's a zero vector, a zero operator, then every vector is orthogonal, obviously, because there's nothing to do there. It's the other way, that's the non-trivial stuff. Okay, right. So now that we have the statement, any questions about the statement? Fine? Okay. So let us look at the proof now. So how does the proof go? The proof says that it does some math trickery, right? So it shows that one can write TU, the inner product between TU and some vector W as follows. So one can write it as TU plus W, U plus W, okay, minus T, U minus W, U minus W. Okay, and there's a normalization of a quarter. And then plus, again, the normalization of a quarter, T, sorry, T, U plus IW and U plus IW minus T, U minus IW and U minus IW. Okay, so is this fine? It's just, and one can check. Okay, so this is sort of this is homework for you. That you can check that the left and right sides, they sort of, it works out, like things will cancel and so on, and then you will get exactly. Okay. And obviously, crucially note that we're using the iota here, right? We're using the fact that we are in the complex space. So we were able to write this expression. In the real space, we couldn't write this expression as it is at least. Okay. So this step is fine. So one can verify these things. Okay. Now the interesting thing is that, so observe that each term, the way it is written, you always have the same vector, right? So these two vectors are always the same, these two vectors are always the same, and these vectors are always the same. Right? So when you take the inner product, it has the form that you have TV, and you're taking the inner product with V itself. It's clear, right, that each term in the expression has this form. Is that reasonable? Okay. Okay. So each term is of the form TVV for some V in the vector space. All right. Now we know that you can hear me, right? No, you can't hear me. Okay, so right. Something wrong with the microphone. You can't hear me, right? It's not working anymore. How about now? How about now? Can you hear me? Did I press something? It is transmitting, I think. It is transmitting, no? Hello, can you hear me now? No. Hello, hi, can you hear me? Okay, so I guess I'll have to shout. It's just the guys in the front, right? The ones behind are anyway not following, so I guess it's anyway better for you. You guys can hear me, right? Is there anyone at the back who was trying to follow? No, right? Okay. Hello, is it working? No. You can figure it out. Okay, so right, so for the people in the front, yeah, I don't know about the attendance thing. We'll see. Okay, we just have a few lectures left, so let's try to get it done. If I'm not audible, tell me, okay, because I don't like speaking too loud. But okay, right. So each term is of this form, right? This we already agreed on. This is fine. Yeah. Okay. Now we know from our hypothesis, right? So the hypothesis says what? The hypothesis says that TUW is going to be 0 for all so okay, what does our hypothesis say? Our hypothesis says that for all v, v is 0, right? This is just from the assumption that we started with, correct? Okay, and so what does that imply? It implies that, can we say something about TUW from this? What can we say? Right, because all terms are of the same form, so it's immediate, right? So this is 0. Is that fine? Okay, and it is actually 0 for all U and W, right? Because we did not make any assumptions on what V and W are, right? Okay, so what does that tell us? It tells us that this implies, is it working now? It's okay. So this implies that TU is, T is a 0 operator. Okay, why is that? Any idea? Right, so TU, suppose this is some, this is some vector, say W prime. Okay, when you applied it, you got some vector W prime. An operator being 0 means what? That it maps everything to the 0 vector, correct? So if TU equals W prime, we have freedom to choose W, right, in the expression. So you can always choose W to be W prime. This is the question you were asking the other day, right? So here you can just choose W to be W prime. And that would give you what? That W prime inner product is 0. And from the properties of the inner product, this can only happen when W prime itself is 0. Correct? So basically saying that, no, where did you get lost? Tell me. So okay, so let's track back. Is this fine? Okay, so here we haven't done much. Okay, so we just said we'll write down the expression for TUW. So this expression is fine, right? Okay, and now in this expression, the hypothesis was what? That the hypothesis was saying that TVV is 0 for all v's. So therefore, this expression must be 0. This is fine, because each term in this expansion, right, will become 0. Because each of these terms is of this form, right? It is of this form, TV. Correct? So it's clear that TU, W will be 0, correct? Okay, good. Now, since we know TUW would be 0, we want to conclude that the operator T itself is going to be 0. Okay, how do we conclude that? We recall what is the definition of a 0 operator. The definition is that when all the vectors that are mapped to by T are going to be 0. Okay? So suppose that when you apply T to U, you got some vector W prime. You don't know what the vector is. But this expression above here, it tells us that this inner product would be 0 for all W vectors. In particular, it would be 0 if you take W to be W prime. Correct? So if you take W to be W prime, and that gives you 0, what does that mean? Okay. Is that clear? Is the argument fine? Okay, fantastic. So great, let's continue on. Yeah, so when the field is complex, right, this argument will not go through anyway. So this argument will not go through, right? If you're in the reals, right, you cannot make this argument. So this argument crucially relied on the fact that you had iota, right, to be able to write it as a combination. So okay, so what was the idea here, right? We were trying to write this expression as a sum of terms of the form TVV, right, for some v's, right? So this you will not be able to do in the reals because we have a counter example. Yeah, but you will have other vectors in the field that would, right? Because it's complex, right? So there'll be other vectors. So you'll not always be able to make them orthogonal to all of them. There'll be other. Is that okay? Any other questions? So let's continue. All right. So now the next result is stating the following. So the next result states that again so when you take the field to be complex numbers, TVV is real for all V. Okay, so it's the same property that holds for all V in the vector space. Only for self-adjoint operators, i.e. T equals T star. Okay, so what are we saying now? We are saying that suppose you took some vector v, okay, you applied the transformation on it, and you took inner product with the same vector v, and you ask, is this number that I get, is this number real or not? Okay, it turns out that it is only real when T equals T star. Okay, that is sort of the statement. So we'll write it down a bit more formally. And again, it says that this result is false for real inner product spaces. Okay, so you can consider any real inner product space, any operator on a real inner product space that is not self-adjoint. Okay, so what is the statement saying here? So the statement is saying here that this inner product would give you a real value for all v's only if the operator happens to be self-adjoint. But this property only holds for complex numbers, right? So if you're real, so if the field is real, okay, you take any take any operator, okay, that is not self-adjoint. Is it making sense? No. So this, okay, you have to be careful with this only for what this means is that it's saying that if you can check the property that TVV is real, right? The only matrices or the only operators for which this property can be true when you're in the complex field is if the operator satisfies T equals T star. Okay. Is the statement clear? Okay. But if you're in the real space, obviously you can take any matrix and the inner product, like you can always find some, so if you're in real space, right? TV would give you a real vector. You take an inner product with V, it would again give you a real number. Okay? You don't have to have T to be self-adjoint. You can take any T that you want. Do you understand what I'm saying? Okay, so this property for complex is not at all clear would be true, but for reals, obviously it will be true, even if T is not adjoint. That is all that we're saying. It's very trivial. I'm not saying anything very deep. Oh, okay. Sorry, yeah. Is the statement clear? Okay, so the statement is that this TVV is real for all V in the vector space. If you're in the complex space, then you have to put some constraint on the T. Otherwise, this property will not be true in general, right? But it turns out if you're in the real space, obviously this property is true for all T's because it's just an inner product in the complex in the real space. Okay, that is all I'm saying. Nothing very complicated. Is that okay? All right. So let's look at the theorem statement more formally. So the theorem statement says that suppose V is a complex inner product, okay, in a product space, and we have T as a linear operator on this space. Okay, so the statement is T equals T star. So T is self-adjoint if and only if TV inner product with V happens to be a real number for all V in the vector space. Is the statement clear? Yeah. Okay. Statement, is it okay? All right. So let's see how one would prove this. Oh shoot, I don't have the proof properly written in this one. Give me a second. With what statement were we on? 7.15. See, 7.15. Right. So this is the statement that we were looking at. So we said T equals T star if and only if, right? Sorry, TV, the inner product belongs to real for all V in the vector space. Right. This is where we were. This is what we wanted to prove. Okay. So let's see how one might consider proving this. So let's make a little bit of space for us. Okay. So I don't know why is it not letting me zoom further. Just give me a second. I don't know why I can't zoom properly on this other one. You can read, right? Or is it too small? Can you read? I'm sorry, for some reason it's not letting me zoom more than this. Okay, so right, so we're going to do the following. So we will say let V be some vector in the vector space. Okay, nothing complicated so far. Then we have the following. Okay, so this is sort of like a small algebraic manipulation. So let's look at it. So we're going to consider TVV and subtract from this the complex conjugate of itself. Okay, why are we doing this? Well, intuitively, we want to worry about this thing being real, right? So we're just subtracting its complex conjugate, and then we're going to try to argue whether when this would be zero or not. Okay, that's what we're trying to do. Okay, so let's write this expression more carefully. So, okay, so this we can write as TVV. So the first part is exactly the same. The second part, when I take the complex conjugate, what will I get? We'll get V and then TV. Is that okay? You just flip the vectors. That's fine. All right. Now we can use the definition of the dual, not the dual. What is it called? The conjugate? No, not the conjugate. What was T star called? I forget. What is T star called? The adjoint. Okay, good. Is that okay? So what have I done from this step to this step? Just use the definition of adjoint, right? Done nothing. Okay, good. This is fine. And now I can use linearity and write down the following. Is that okay? Making sense? Okay. So this is the part that we're going to be focusing on now. Okay, that the basically the imaginary part essentially, right, of the inner product would just be T minus the adjoint and the inner product with V. That is what we're going to do. Is that good? All right. Now, so let's start with the so there's equivalence, right? So we have to show both directions. So we're going to assume, so for the upward direction, we're going to assume TV, sorry, the inner product with all V's belongs to real. And from this, we want to conclude T star equals T. That's the direction we want to do first. I think so, yeah, okay. Right, so we are given this, that TVV is a real number. Okay, now let's look at the right-hand side. The right-hand side on the LHS is 0. What have I written? The right-hand side in the equation. Yeah, okay, let me write it down. So, okay, so let's look at the right-hand side. Okay, so we want to conclude. So, okay, so if the RHS was equal to 0, then we were very close to proving what we wanted, right? Because we have some operator, VV on both sides is disappearing, right? Is disappearing. And therefore, we would probably be able to argue that T minus T star is 0, right? Something along these lines. We may be able to do. So we have to still think about it. Okay. So let's see. What about the LHS? So given that TVV is a real number, the LHS is what? It was the imaginary part, right? So the imaginary part is 0, obviously. Correct? So LHS is 0, right? Which implies that the RHS also has to be 0. Okay. And now what do we conclude? So we have T minus T star acting on V is giving you 0 for all V in the vector space. Correct? So far straightforward. As you're lost, what happened? Tell me. Is it making sense? Okay. This is fine. Now we want to conclude from this, we want to conclude that T minus T star is 0. But this is not obvious, okay? So you have to use one of the results that we proved earlier. So we proved that, so for a self-adjoint operator, let's call it say T tilde, okay? If you have T tilde V is 0 for all V, it implies T tilde is 0. Okay, so let's double check theorem 7.14. Okay. So we said that TVV is 0, right? This is the theorem we just proved, right? So if TVV is 0 for all v, then the operator t has to be 0. Yeah. Yeah. That's the thing I was checking. You don't need to assume that. You're absolutely right. Okay, so the important thing here is there are lots of closely related statements. We'll see them later. Okay, so don't confuse. I myself got confused, but you guys have to be careful, okay, because you have to write exams. So um, the important thing here is that you have to be able to check it over the field of complex numbers. Okay, so if over the field of complex numbers TVV is 0, then you conclude T is 0. Okay, if you only given it for reals, you cannot make that conclusion. Okay, that's the important part. So this is what I messed up here. So it's good that that we checked. So here we don't have to assume anything about self-adjoint. Okay, so you just all that you care about here is that. So theorem 7.14 says if you have say t tilde v0 for all v in the vector space, but this has to be over complex, over the complex field. Okay, that is the important point. Is that okay? And this exactly is of that form, right? We have, so the vector space is complex, we're guaranteed that already. And this is some operator. Okay, and we're guaranteed that TVV is 0. So we can call this T tilde. So we guaranteed T tilde V is 0, and so therefore we conclude T tilde must be 0. Is that fine? Okay, all right. Now let's do the other direction. So the other direction is what? The other direction is T star equals T. Okay, and from this we want to conclude that TVV must be real, right? This direction is much simpler, right? Because already on the RHS now, so the RHS vanishes. Why is the RHS 0? So this is the RHS, right? So RHS is 0 is clear because T minus T star is 0. So it'll give you a 0 vector, and a product with a 0 vector is 0. And what does it tell you about the LHS? So this implies the LHS is also 0. And what does it say? It says it's real, right? The complex, the imaginary part is 0. So imaginary part of TVV is 0 for all. Done? Reasonable? Yeah. So, okay, so in the second part, what do we want to show? We want to show that you're given that T equals T star. So you're given that it's self-adjoint, right? And we want to argue that this inner product, TV, V, would be 0, would be real. So the imaginary part would be 0. So how do we do this? We look at this equation, right, that we had in the beginning. So this is the left-hand side. This is the right-hand side, right? Okay. And in the right-hand side, we are given the T minus T star. So we are given T minus T star is 0, right? Because T equals T star. So what can you say about the right-hand side? Right, so the right-hand side is 0, that's fine. The left-hand side is also therefore 0. Okay, and what is the left-hand side saying here? Is it saying anything about the imaginary part? Right, so the imaginary part is 0. Got it? Okay, any other questions? Good. All right, so let's continue. All right, so on real inner product space V, a non-zero operator T might satisfy TV V is 0 for all V. Right, this we already saw. This can. However, the next result shows that a self-adjoint operator cannot have such a property. Okay, so if you additionally impose that you're looking at self-adjoint operators, okay, then even if you're real, you would not be able to satisfy this property for all. Is that okay? So earlier the statement was too weak, right? We were just saying that if the inner product vanishes, can there exist a non-zero operator or not? And we found that obviously there would be trivially non-zero operators such that TVV is 0. So we had to strengthen the hypothesis, and now we've strengthened it by saying that the operator T is self-adjoint. Okay. Now if the operator T is self-adjoint, then the only way you can have TVV is equal to 0 is if T itself is 0. Making sense? No. Okay, I'll give you a second. You can think about it. So we saw right in that example earlier that if you have a real inner product space, you can have a non-zero t. So one can have a non-zero t. So in real spaces, right? Non-zero t such that TVV is 0 for all. Correct? We had that example. We can take any non-adjoint matrix, right? Like, huh? So say it again, TV plus. Yeah, that's what I'm saying, non-zero operator. That is what a non-zero operator is, right? What you're describing is a zero operator, TV equal to 0 for all. Of course, that will satisfy. That will satisfy. We're asking, is there any non-zero t that could possibly satisfy this? And we saw that the rotating example, right? That everything would be orthogonal and you would get that property, even if it's non-zero. So you have to be careful, right? So we want to be able to use the fact that if you have this property, when can you say that the operator t is 0 itself? Okay. One thing was, of course, that instead of looking at reals, if you could look at the complex field, then it is the case. That was one thing that we tried. What if you could only test on reals, right? Then the point is that if you additionally impose, that t star equals 3, like it is self-adjoint, then also it becomes the case that it has to be 0. If t equals 0. Is that right? Okay. So let's see what the statement says. So here I think it'll become more clear. So it says suppose that t is a self-adjoint operator. So t equals t star. Okay, so suppose in the case. Which satisfies TV v is 0 for all v. Then t is 0, and we can add for emphasis regardless of whether the field f is real or complex. Right? Because already for the complex case, we proved, even without the hypothesis, we already proved, right, for the complex case, which is the mistake I was making, which you pointed out. Right? So in the complex case, it's already proved. We really need to worry about the real case. Is that okay? All right. So the next theorem, it says, showed this already without the self-adjoint hypothesis. Now we need to show the result when the vector space is real. Fine. J, is it making sense? Did you get lost? Tell me, where did you get lost? Is the theorem statement okay? So the theorem statement is saying, suppose you have a self-adjoint operator, okay, and it satisfies TV v is 0 for all v. Then we want to conclude that t equals 0. In fact, we can conclude that t equals 0. If you remove this, then the statement is not true when you're looking at real spaces. Remember the counter example with 90-degree rotation. Okay, that is the statement. How do we prove the statement? So that's what we're going to do. So for the complex case, do you agree with, oops, sorry about that. So for the complex case, do you agree we don't have anything to prove? Right, because we already showed that even without the hypothesis, the statement is true. Okay, so now we're going to look at the real space when the vector space is real, and then we'll see how to prove it. If the vector space is real, then we're going to do the following. Okay, so if the vector space is real, so suppose f is the real space. Okay, and now here comes like the clever bit. So we're going to write TUW. Okay, again, we want to write it as a product of terms of this form, TVV. If you want to write it with like over some set of these. This is the thing that we want to write the left-hand side as. Correct? So how do we do this? So they've done the non-trivial part. They've said that you write it as follows. So you have U plus W. There's a quarter. Okay. And then minus T U minus W, U minus W. Okay. So the expression is fine. How do you prove this? So this we sort of have to be a little bit. Okay, so this is basically just computation. You're going to simplify it like you did the last time, but you're going to need 2 extra properties. Okay, so you're going to use the fact that TWU equals WTU. Okay, and when you write this, what are we assuming? Exactly, right? Because in general there would be a T star on the other side, but here we are assuming, so we are using T star equals T. This is why you couldn't write it in the without the assumption. Okay, you couldn't write it as a sum of TVV. To be able to write it as a sum of TVV, we're using the property that T star is 2. Is that okay? Okay, that's the crucial observation. And the next part is just you're working in real space, right? So complex conjugation doesn't change anything. So WTU is the same as TUW. Okay, so you're going to use this fact, and then you just calculate and use 1 and 2. Okay. Yeah, the second point is saying what you tell me. So here, what have we written? We have written a vector, say, let's call it V1, V2 in a product. If it's the same as V2, V1, right? What does that mean? That the complex part is the same, right? It can only happen if the complex part is 0, essentially, right? Otherwise, because that's the plus minus side. It's just a complex conjugation. But the point is, we are already in the real space, so it doesn't matter. It's going to be the same. Okay. In general, this thing is the complex conjugation. But we're in the real space, so it doesn't matter. Is that fair? All good? Okay. So, right, so we have written it, and then that's basically the bulk of the argument, right? Because once you have written TUW as TVV, right, then we know from our hypothesis that the right-hand side is going to disappear, right? Because we assume that the operator is such that TVV is for all. Okay. So, right, so let's see how so this part is fine. Okay. So what are we arguing? We are arguing that the right-hand side. So basically, we are arguing that TU. So the right-hand side is 0. This is the right-hand side. Okay. This is what I'm calling the right-hand side. So this right-hand side is 0 from hypothesis. Is that clear? Yeah, straightforward. Okay. So TUW is going to be what? This is also going to be 0 because that was the left-hand side. Right? All right. And this is true for all U and W in the vector space. Correct? Okay. And now what do we want to conclude? We want to conclude that T is a 0 operator. How do we do it? It's the same old trick. So TU is going to give you some vector U prime, right? And you set W equals U prime. So what will you get? You'll get U prime, which is the norm of U prime is 0, which means what? That U prime itself is 0. Right? Which means that T is mapping all vectors to the 0 vector, which is the definition of a 0. All good? Yeah. Okay. So that was theorem 7.16. Yeah, I know it's non-stop, you guys, but we're making progress. We're almost there. Okay. So now we're going to look at something called normal operators. All right. So a normal operator is sort of very it has very, very nice properties, which we're going to look at in a little bit. But for now, as most things in abstract stuff, we're just going to define it first, and then we'll see why it's a useful notion. So we say an operator. So an operator T, an operator on an inner product space, okay, is normal if it commutes with its adjoint. So what does that mean? So if you have an operator T, okay, what does commute mean? You can write it in whichever order, right? The multiplication. So you have T and T star. If they commute, what would it mean? This would be equal to what? T star T. Right? You can move them around. Is that okay? The definition fine? Making sense? Right? Okay. All right. Now, so suppose, okay, so now that you understand the definition of a normal operator, suppose T is adjoint. T is adjoint. Okay. Is it normal? Ah, yeah, self-adjoint. Thank you. Is it normal? Right? Why? Exactly. And everything commutes with itself. Okay, that's reasonable. Okay. All right. Now let's look at an example here. So it says that we are going to take T to be this matrix 2, -3, 3, 2. Okay, and what we want to do is we want to argue that T is not self-adjoint, okay, but T is normal. Okay, so how do we check whether something is self-adjoint or not? You compute the adjoint. So how do you compute the adjoint? You just compute the complex conjugate transpose and then complex conjugate element wise. Correct? So how do we do this? So here it would be 2, 2, and you take the transpose, so you had minus 3, 3. Okay? Is that fine? There's nothing complex, so there's nothing to conjugate. So is this self-adjoint? It's not, right? Because T and T star are different. So it's not. So T is not equal to T star. So T is not self-adjoint. The example is basically saying the opposite, right? Like we said, if it is self-adjoint, then it is normal. Now we're looking at an example where it can be normal, but it's not self-adjoint. That's all the example is illustrate. Correct? So we have this. Now we have TT star. Now the rest of it is a little bit of calculation. Okay, so we are going to skip that calculation and just believe the text for now. That when you compute T star, T and TT star, in both cases, you're going to get 13, 13 along the diagonal. This is a calculation you can check. Okay, and what does that mean? It doesn't matter which order you multiply. Okay, reasonable? Any questions? Good. All right. So that's good. And now the story is as follows. So in the next section, we will see why normal operators are interesting. Because I gave you some definition. I showed you how it's a little bit related to being self-adjoint. Okay, but why it's actually useful, we will see in the when we're characterizing the when we look at the spectral theorem and things like this. Okay, so it has like very clean characterization of operators and so on. Okay, so for now, let us try to understand some basic properties of normal operators. So that is what we're going to focus on mostly for this lecture. Okay, if you have some time, maybe we can start the spectral theorem, but mostly we'll focus on this between these properties. So here's a very beautiful characterization of these normal operators. So what does it say? It says that T is normal. So T being normal is equivalent to checking whether TV, the norm of TV is the same as the norm of T star V for all V in the vector space. Okay. Right, like because on the one hand, the definition of normal was that something about commutation, T star, T star T. And here it's just flipping the script entirely. It's just saying that you'll be looking at the norm. You take any vector V, you apply T on it, you look at the norm, it has to match the norm when you apply it on T star. Okay, apply a T star on it. So I always say that. Right? So it's very unusual, and the proof is actually kind of straightforward. So let's see how the proof goes. First of all, is the statement okay? Yeah. Oh man, yeah. Sorry. Yeah, interrupt me, okay? Because I'm not used to speaking so loud, so it's a little bit harder. It is a little bit harder. Okay. Right. So suppose that T belongs to so T is a linear operator. Yeah. And is it okay now? Okay. So, and what we're going to do is normally what we do is we prove one direction and then we prove the other direction. Okay. In this case, we're going to prove both directions at the same time. How do we do it? Right. So we're going to look at the definitions. T is normal. Okay. This statement is equivalent to saying what? The T star T minus T star is 0. Because this is the definition, right? Is that okay? Is the first step fine? Okay. Next step says what? It says that this, in fact, is equivalent to saying that T is, sorry, give me a sec. Yeah, let me write it in. Right. Apologies, my board work is a little bit shoddy. Okay, right. So we have T star T minus TT star is 0, right? This is fine. That in turn is equivalent to what? It is equivalent to T star T minus TT star acting on V with V 0 for all V in capital. Why is that? What? You have to be loud now. You asked me to be loud. You also have to be loud. Yeah. So one direction is clear. The other direction. Exactly. So what did we show? We showed that, look, the first thing we want to check is, do we know that the vector space is complex? Here we don't, right? We're not making any assumption. If the vector space was complex, you could immediately assume this. This is correct, right? But because the vector space is not complex, it is real. We said something similar still holds if you have some condition on the operator. What was the condition on the operator? Has to be self-adjoint, right? Now, is this thing self-adjoint? Okay, it turns out that it is. Okay, how do you see this? Because when you take the star, the order will flip again. Okay, so let's do that. So t star t minus tt star. When you're taking the star of the whole thing, right? You're going to get what? You'll get t star minus t star. And when you take the star, you will have what? This operator, it's star, but it comes first. This operator, it comes afterwards. And t minus this operator, its star would be itself, and then t star. Okay. It's not obvious immediately. You can, this I leave as an exercise. Okay. Okay, let me write it down. So this is homework for you to check that t star t minus tt star is self-adjoint. Okay, for now you can believe me. You can go home and do the calculation at peace. You don't have to rush it. Assuming it is self-adjoint, right? We just proved, right, a few seconds ago that in that case, we don't need to make any assumptions about the vector space. It can be real or complex, doesn't matter. In both cases, one can conclude that t star t minus tt star has to be 0. Is that step okay? Okay, that is why we were like building all these things, right? So they're kind of fitting into each other. So you have this result, and right. So we have oh, what did I do? I wrote the same thing again. So the fact that tt star minus this object being 0 is equivalent to this, right? That was basically the theorem state, which is what we wanted to prove. Sorry, I wrote the same thing again. Apologies. Is that okay? Fine. Okay, now let's expand this further. So we would have t star t. V is the same as tt star vv. It's just linearity, right? So we're just expanding it. And now what can we write this as? We can write it as tv, the norm of this object. Why is that? Why is the last step true? Yeah, okay, so let's use the definition of the adjoint, right? So you have TTVV. Okay, if I want to take this operator to the other side, what will I get? The adjoint of T star. We know that the adjoint of the adjoint is itself, right? So you're going to get TVTV, correct? It's just similar to the other side. There's nothing complicated. Yeah, is that okay? All right. And similarly for the other one, right? So if you have TT star V, how would you take it to the other side? Now here's the most standard one, right? Like you just put a T star. Is that okay? So then you basically have norms, and the norms match. And remember, each step was an equivalence. We did not say that, you know, it's only one direction. We showed each step is equivalent. So basically you end up with the fact that T being normal is equivalent to just checking that the norms match. The last step. Okay, yeah. Let's look at it again. So here, what were we trying to argue? We were trying to argue that, so we want to say that T star T V V. Yeah, let's look at the one on the right, actually, it's easier. So let's look at TT star V. Okay. Let's call this vector W for the moment. Okay. So you have TV, TW in a product with V. What is the definition of the adjoint of T? The definition says that if I take any W and V, then I can write T star on the other side, and it would give me the same answer. Right? That's what the definition of adjoint was, right? That's all I've done. Right? So when you do this, what do you get? So you replace W back to being what? T star V. Right? And so now suddenly what do you have? You have an inner product of a vector with itself, which is what? The norm of the vector. Right? Reasonable? Okay. So this basically gives you the proof that we wanted. Okay, that being normal is equivalent to checking that the norms are the same. Any questions? Good. Yes. Oh, because you have to do if and only if, right? You also have to show backwards. You have to show that if that statement, so if this statement is true for all vectors, we want to conclude that the operator itself is zero. It's for that direction. One direction is obvious, exactly. You're right. If you know that the expression is zero, then if the operator is zero, then of course the inner product will be zero. It's the other way, right? Okay. Any other questions? Reasonable, making sense? Okay, good. So we can continue further. Right. Okay. So now, so exercise 2, I don't think we've looked at this. It's my job. I think I'll add it as a homework at some point. But the exercise states the following. It states that eigenvalues. Okay, so let me write it down. So exercise 2 states that eigenvalues of T star, the adjoint of each operator. So if you look at this set, right, so you're looking at the eigenvalues of the operator T star. This actually is going to be the complex conjugate of the eigenvalues of T. No, I think I wrote it the other way. That's the statement. Okay. So you take the operator T, you look at its eigenvalues, you get some set. Right? You look at the operator T star, you look at its eigenvalues, and you take their complex conjugate. Okay. These sets are going to be the same. Is the statement clear? Okay. All right. Now, what the text is trying to motivate is that here we did not say anything about eigenvectors. We just said that the eigenvalues are going to be related by complex conjugation. Okay, we didn't say anything about eigenvectors. Now, if we wanted to say something about eigenvectors, we would have to make some assumption about T, because in general, the eigenvector will change. Okay? So when you take T and T star, the eigenvectors can change. It is saying that if you additionally know that the operator is normal, okay, then one can also say something about the eigenvectors. Is the motivation clear? Poor thing. So, okay, so eigenvalues of this are complex conjugates of the eigenvalues of this operator. Yeah, I mean, it doesn't really matter though, but yeah, sure. I also got confused. It's okay. Yeah. Yeah, I mean, if A equals B conjugate, then A conjugate is B, right? That's right. So if A is B conjugate, then A conjugate is B, right? That's fine. It doesn't matter, but okay. That's good. I was not compiling for. Okay, any other questions? Okay, so now what we want to do is the question is, so let me write it down. So it does not say anything about the eigenvectors of T and T star. To do that, and okay, and they can be different, and they can be different in general. Okay, so can be different in general. So to say something about the eigenvectors, we look at normal operators. Is that okay? That is sort of the high level motivation for what we're doing. Yeah. Okay, so let's look at this. So here's a quick corollary for a corollary of the thing that we showed now about the inner product. So one of the corollaries is that we're going to be able to say something about the eigenvector. So it says the following. So suppose that T belongs to a set of linear operators on the vector space capital V. Okay, so is normal. So is such that T star T, T star T is the same as TT star. Okay, so we're assuming that you have some operator that is normal. Oh man, I'm so sorry, you guys. I know it's hard, but they shouldn't have 1.5 hour lectures. It's bad. Okay, so the vector V is an eigenvector. So suppose it is the case, because you have some normal operator T, okay, and V is an eigenvector of this. Is an eigenvector of T with eigenvalue lambda. Okay, so TV is lambda. Right, this you're given, for example. The claim is that V is such that T star V would give you lambda bar V. So V is also an eigenvector of T star, and it will give you eigenvalue lambda. Okay. The exercise just said that the eigenvalues are related by complex conjugation. Here it's saying that the eigenvector remains the same. Okay. So in the previous thing, right, he said that the eigenvalues of T star and T are related by conjugation. Now, if you additionally know that it is a normal vector, it's a normal operator, then you also know that the eigenvectors are going to be the same. Is that okay? Shall we move to the proof? Is the statement clear? Any questions about the statement? Okay. All right. So let's continue then. The proof is kind of very cute because of that characterization that we had. Okay. And how does it go? It basically considers T minus lambda I, our favorite operator, because the null space of this would give you the eigenvectors for lambda. Right? This we already showed in the previous lectures. Correct? Okay. So right. So what we're going to do is we're going to apply the theorem. Okay. So we're going to consider T minus lambda I identity. Okay. And note this is using theorem 7.2. Oh no. Are you okay? Do you need water? Do you have water? All right. So we're considering T minus lambda I, this operator, and we're going to use the theorem, right? So the theorem said what? The theorem said that because T is a normal operator, it is going to be the case that whether you look at, let's recall the statement. So it was saying that if you look at TV, it's norm, or you look at T star V and it's norm, right? These are going to be identical, correct? That's what this is. That's it, right? Or am I saying it wrong? 7. Yeah, it's correct, right? So TV, an operator being normal is equivalent to saying that for all vectors, TV, the norm of TV is the same as the norm of T star. Right? This is what we said. Okay. So now we're going to apply that property to T minus lambda I. So let's do that. So we're going to write T minus lambda identity. We look at it on the vector V that we were given. Right. So V is an eigenvector, remember? Okay. So this is going to be what? It would be T minus lambda identity star V. Because why? Because the operator is normal, right? And that in turn means what? That we can write it as T star minus lambda bar identity acting on V. Is that okay? Okay. So what does that mean? It means that the length of this vector is 0, right? Because this was 0. It's an eigenvector. Right? So the left hand side is 0. Why is the left hand side 0? Because V was an eigenvector of T with eigenvalue lambda. Right? So therefore the left hand side is 0. This is fine. That also means the right hand side is 0. And what does that mean? That in turn means that T star minus lambda by identity V has to be 0 because V is a non-zero vector. Correct? And what does that mean? That implies what? What does it say about T star V and lambda bar? It says that T star has, right, an eigenvector V with eigenvalue lambda bar. Correct? Is that okay? No. It's fine? Right? Okay. So it's kind of nice, no? I mean, you are making like we're finding fairly non-trivial statements, but we're using that very clean characterization about norms. Turns out to be very helpful. And it's particularly helpful because why? We were looking at the null space, right? Somehow we were looking at things that are mapped to 0. And when you have norms, it really helps you argue about things that are mapping to 0. Right? That is sort of the high level thing. All right. So let me move this again. Okay. Good. Let's make some more space. So moving on, since every self-adjoint operator is normal, right? The next result in particular applies to self-adjoint operators. Okay, so anything we prove about normal operators, that immediately applies to self-adjoint operators. That's all it's saying. Nothing. You can't hear me? Oh no, really? In my head, I'm being super loud already. Oh. Did this magically start working? It did. What the hell? Okay. Doesn't matter. Technology. Right. So corollary 7.22, it says orthogonal eigenvectors for normal operators. Right. So let's look at this. So corollary 7.22 about orthogonal vectors for normal operators. Right. So what is the statement? The statement says the following. So suppose that T is some normal operator. Okay, so it's normal. It's a normal operator. Normal operator T star T is the same as T star. Right? That's the definition of a normal operator. Then the eigenvectors of T corresponding to distinct eigenvalues are orthogonal. Okay. So far we did not make any connection between distinct eigenvalues and orthogonal. Okay. Now it's the first time we're able to say something very interesting. We're able to say that if it is a normal operator and you find two eigenvectors for distinct eigenvalues, you can show that they would be orthogonal. Okay. And I leave it as an exercise to check that if it's the same eigenvalue, then you can't say anything. Okay, because it has to have degeneracy, then it has to multiple same eigenvalues, then it's not obvious that they have to be orthogonal. Okay, so that is, it has to be distinct. Okay, so this part is important. Distinct eigenvalues. Is the statement okay? Okay. Right. So now let's see how to prove this. Okay, let's see. We're going to be able to start this spectral thing. Okay, we only have 5 minutes. Okay, let's see. Right. So suppose that suppose alpha beta are distinct eigenvalues. Okay, so two distinct eigenvalues, not a big deal. Okay, and UV are the eigenvectors, the corresponding eigenvectors, right? So you have alpha beta as eigenvalues, UV as eigenvectors. Right. So therefore, what you have is Tu is alpha u and Tv is beta u. That is what it means to be eigenvector, eigenvalue pairs, right? Not done anything so far. Okay, now we're going to make some nice observations. So the first observation says that using corollary 7.21, we conclude what? So what was corollary 7.21? It was saying that if you have normal operators, then the eigenvalue for T and T star are related by complex conjugation and the eigenvector stays the same. Right? This is what we just proved using the norm thingy, right? Like we just proved the second one. This statement, right? We said that if you have V as an eigenvector and lambda is the eigenvalue, then T star will also have the same eigenvector, but the eigenvalue would be complex conjugate. Correct? This is what we just showed using the norms, right? Like the very nice characterization using this. So we're going to use that fact now. So we're going to say that using this corollary over here, since V is an eigenvector of T, it is also an eigenvector of T star, but with eigenvalue beta bar, right? The complex conjugate. Is that good? So far, so good? Yeah? Good. All right. So now what are we going to do? There's some calculation now. So let's look at the calculation. So the calculation says the following. It says we're going to take alpha minus beta UV is the same as alpha U V. Okay, let me say something. Okay, so why are we starting with this expression? Let's think about it for a moment. What do we want to do? We want to somehow argue that, so we know first of all that alpha and beta are distinct. Correct? So this term will never be zero. If we are able to somehow show that this expression is zero, then what would we have established? That U and V are orthogonal. Okay, because the definition of orthogonality is that the inner product disappears. Okay. And we have this alpha beta, and we somehow want to use the complex conjugation and so on. That is sort of the high level idea of what we're trying to do. So let's expand this. If you do that, we would get alpha u v minus u beta bar v. Is that okay? I skipped one step. Right? So I just took beta from the left hand side and put it on the right hand side. That's all. Is that okay? Moved beta. That's all I did. Yeah. Yes. Okay. Now, okay. So now alpha u we can write as Tu acting on V. Sorry, inner product with V. Inner product with V. And the second expression we can write as what? Now this is the part that we just observed here, right? So V conjugate multiplied by V can be written as T star acting on V. Correct? The complex, the adjoint, right? Okay, this is good. And so we're getting close. So now we have TUV minus, now we can use the definition of the adjoint. Right? What is the definition of the adjoint? It just says that I can move the operator T to the other side. We'll get TUV. Okay? Right? You see the magic? Okay, and then this will disappear. Okay, and we already argued that since alpha is not equal to beta, therefore the inner product has to be. This is like magic. I don't know how to take a word. Everything sort of checks out. Okay. Okay. So before we conclude for the day, let me just tell you what the spectral theorem, the statement is, because the statement is kind of clean. We'll do the proof later. It's just 2 minutes, right? We have like 2 minutes. Right. So the statement for the spectral theorem is very, very simple. It just says the following. So you look at the complex field, okay, and you look at any operator T. Okay, then these statements are equivalent. So the first statement is T star is T star T, which is that it's normal. Okay, this is equivalent to saying that there exists an orthonormal basis consisting of eigenvectors of T. Okay, so it's basically saying if you have a normal operator, okay, then there would exist, it's guaranteed that there would exist some orthonormal basis which would essentially each correspond to an eigenvector of the operator. It's a very strong characterization to think about it. Right? And this is essentially the same as saying that there's like an orthonormal basis in which it's diagonal. Yes, diagonal. Okay, so remember in the beginning we were saying that diagonal is like one of the most simple forms of things that we can have. Now here we've like basically come full circle. We're saying that if an operator is normal, then not only can you diagonalize it, you can diagonalize it using orthonormal vectors. Like one of the really nice things. We'll look at the proof next. Thank you.